So as we wrap up this module on convergence, we're going to focus finally on the endpoints. So we're going to go back a little bit to the ratio test and getting intervals of convergence. And our intervals of convergence were always less than or like between, but not equal to. And we could never tackle the equal to until we had all the other tests. So now that we finally have all the other tests, especially harmonic and alternating harmonic are going to be key. Now we'll be able to look at our intervals, and are our intervals of a convergence open or are they closed? They start out open. That's what you've done so far. All your intervals have been open intervals of convergence. Today we'll be talking about, can you close either end? Okay. All right, so we've got, just to set everything up as we review, if we are not dealing with positive terms, then your job, once you find your limit, is to check the absolute value. If you don't have positive terms. Actually, absolute values will come down here. So you want absolute values for the limit. Absolute values for the limit. Absolute values for the limit. All right. Can you keep it all straight? The limit has to go in what direction? Greater than 1 or less than 1 if we are reviewing absolute convergence. Okay, less than 1. So diverging if greater than 1 and inconclusive up till this point if it's equal to. We also talked about the difference between conditional convergence and absolute convergence. In absolute convergence, we have the idea that both the series with and without the absolute value will converge. That is absolute convergence. That means if I've got it or if I don't got it, no matter what, it will converge. Conditional convergence is when only the series without the absolute value converges, but with the absolute value, it doesn't. So that's conditional convergence. Only one, but not the other. We talked about last Friday the alternating harmonic series. Does it converge or does it diverge? All right, well, by definition, the alternating harmonic series, we said, is a convergent integral. Okay, we proved it, and we said that this one converges. But to find out if it's going to be conditional or not, we have to check what will happen to this same summation if we include absolute values. Yeah, this is why. It's conditionally converted. It'll turn out to be that way. Okay, if we throw that on there. So the proof is, okay, if we absolute values, if we look at -1 to the n plus 1 by itself, and we look at 1 over n by itself, all right, what will the absolute values do to the term that has the -1 in it? Okay, if it has the absolute values, what will that do to that? It's going to always be +1, okay? So then that gets us to this. Okay, what about 1 over n? Will that ever be negative? Nope, it'll never be negative. So then I get the same thing. I don't need the absolute values, and I just get 1 over n. So with the absolute values, this becomes the harmonic series, which diverges. So because one of the series without the absolute value converged, but with the absolute value it diverges, then we say the alternating series converges conditionally, and the condition is that it needs the absolute value to force it to converge. Without it, it doesn't. That's why we say it converges conditionally. The condition is the absolute value is required. The absolute value causes it to diverge. So the condition is that we don't have absolute value on there, that we keep the alternating. All right, all that to set up this point. Endpoints of a power series. Ordinarily, we have stopped at this point. Okay, we've gotten to the point where it's an open interval, where we have a center, okay, that one's centered at 0, and we have a radius, but our endpoints, like maybe it's 2 to 7, but it's between 2 and 7, not including 2 and 7. So now we want to test whether the endpoints themselves are convergent or divergent. So we're going to do this part. Test for convergence or divergence at the endpoints. And we're going to use all the tests we have available to us at this point. And then we'll know if the endpoints are going to include the little equal bar to or not. It'll either be greater than or equal to, or less than or equal to, or not. So let me show you how that works. All right, we start with the ratio test. Okay, we just want to start with that, and we want to get our interval of convergence. So we want to identify if there is a common, if it's geometric, does this have a common multiplier? If it's not geometric, we go right to the ratio test. This one's not geometric, so we're going to go right to the ratio test. So the limit of my ratio test will be set up like this. I'm going to have -1 to the n plus 2. I'm going to have x to the 2 quantity n plus 2 over 2 times, 2 quantity n plus 1, which will turn into n plus 2. There we go. All right, there's my first term. That's my n plus 1 term. And then I'm going to multiply by the reciprocal. So I'll have 2n. I'll have -1 to the n plus 1. And I'll have x to the 2n. So now let's set about the business of reducing this so we can look at what's going to all happen. All right, so let's look at reducing the -1s. Okay, so Kaylin, if you reduce those, what will you be left with?
1.
How do you get that? They're not the same thing. The only way they'd be 1 is if they were identical. They're not. One's n plus 2 and one's n plus 1.
I guess -1.
Well, which one has more -1s in it?
Top one.
The top one. How many more -1s does it have?
1.
One more -1. Okay, so it's not a positive one. There's no absolute values here. Okay, this is just a -1 to the first. Okay. All right, Juliet, do the x's. Yep. Okay, so we get x squared. All right, and Rain, do the final ones.
Well, wouldn't it just be 1/1 because you would do L'Hopital?
Yeah, I'll catch up to you, but it's going to start out as 2n over.
2n plus 2.
Okay.
And then when you put infinity in, it's infinity over infinity.
Yep. All right, so let's kind of look at what we've got left here. The -1 is a constant, so we can pull that out to the front. So that'll be -1 in front of our limit. And then we'll have the limit as n approaches infinity. And we'll have left in there x squared, and then to what Rain's point is, infinity over infinity, and then we do L'Hopital, so we get 1. So we end up with a negative pulled out, and then x squared. So now we want to solve for the interval. So this will be the absolute value of -x quantity squared is less than 1. And we do the math. And we get -1 less than x, which is less than 1. Okay, that's all old stuff. So So we have our interval of convergence. Now, we need to investigate what happens at 1 and -1 exactly. We know that it's going to converge if it's between -1 and 1. If x, as long as x is between 1 and -1, then this power series will converge. But we need to investigate what's going to happen if x is actually equal to 1. And what if x is actually equal to -1? Then what happens? So I'm going to slide over a little bit, give myself a little room on the side, and I want to look at checking my endpoints. So if x equals -1. So go back to the beginning, the very beginning, and look at this power series and change x to actually be -1. We're substituting in -1. So my power series is the sigma as n goes from 1 to infinity of -1 to the n plus 1. And then x is -1, so that would be -1 to the 2n. And then, did I have a denominator? Yeah, over 2n. Okay, so if x is -1, then I'm just going to plug -1 right in. Now you look at each piece and what's going to happen. So we look at this first piece. Yeah. Okay, very good. -1 to the 2n. We know that 2n is always going to be what kind of number? Even. 2n will always be even. And if the power is always even, then what will happen to -1 in the parentheses? It'll always be positive. So this whole part right here is going to be replaced with 1. Okay. Pause. Okay, so then that's 1 because it's an even power. Are there any constants I could pull out to the front of this sigma? Okay, let's pull out 1/2 to the front. Okay, so then I'm going to have 1/2 pulled out to the front of this sigma. And what's left? -1 to the n plus 1. And 1 over n. Do you recognize that? Kaylin says yes. What do you recognize it is?
Alternating harmonic series.
It's very good. So this is the alternating harmonic series. Even though it's multiplied by 1/2, still the alternating harmonic series. So what do all alternating harmonic series do? Alternating harmonic. Okay, what do all alternating harmonic series do? Converge conditionally. That's right. We just proved that on the slide right before. So since they converge conditionally, I can go back to my inequality and I get to include -1 because this is the interval of convergence, and at -1 itself, it will still converge. Even though it's conditionally, it still converges. So I get to include -1. Now, do I get to include +1? All right, well, let's check that. So let me slide back over here. If x is equal to +1, then what happens? So start over. So if x itself is equal to +1, I get -1 to the n plus 1 times +1 to the 2n over 2n. And I check this out. All right, what happens to this? It's still going to be 1. And can I pull a constant out to the front? Yeah, so I get 1/2 out in front of still times 1/n. I still have an alternating harmonic series. So the result is still an alternating harmonic series. And so since that will converge, then I can also include, so the summary is that as long as I pick x values that fall between -1 and +1 inclusive, then this power series up at the top will converge. If I say pick x to be 1.1 or anything outside of that interval, then this power series will diverge. So this will converge on the condition that it will stay within the convergence interval. Now that was an example where both endpoints turned out to be alternating harmonic. So they both converge. Not every example is going to be like that, like the one we're going to do next. All right, so we want to apply our ratio test and come up with our convergence interval. So we'll have x minus 3 to the n plus 1 over 2 times n plus 1 times 2n over x minus 3 to the n, and then we reduce. So as I'm reducing, I'll get x minus 3, and then I'll have 2n over 2n plus 2, which L'Hopital will get me 1, so I'm just left with x minus 3. So the result of my ratio test is x minus 3, which means x minus 3 has to be less than 1. Which means x minus 3 needs to be bounded between -1 and 1, which means x needs to be bounded between 2 and 4. That's my initial interval of convergence. Now I want to check my endpoints. What if x is actually 2? And what if x is actually 4? So we'll check both of those things. So I'll make myself a note. I'm going to check my endpoints. How could you imagine that they might check this like on a multiple choice?
They have the same interval, but with like less than or equal.
How many different ways could you write this interval? 2 to 4. It could be 2 to 4 with no equal to bars under it, or it could be 2 to 4 with equal to bars on it, or 1 on either side. So 4 altogether, and so you got to pick the right one. So you could do all the work and you could get down to 2 and 4, but unless you know how to finish it by checking your endpoints, then you're going to be stuck. All right, so let's check it. So if x is 2 and if x is 4, what would happen? All right, so if x is 2, we start over with the original series. So if x is 2 and I plug 2 in for the x right here, what will I get? I'll get -1 in the parentheses. So I will get -1 to the n over 2n. Well, that's starting to look really familiar. Okay, I can pull the half to the front, and I'm going to get -1 to the n times 1 over n. All right, and everybody's like, okay, I recognize that. I'm getting to be a pro. We see that as what kind? Alternating harmonic, which means it will converge. So I can go back to my interval and I can include 2. All right, but what if it's equal to 4? If x is equal to 4, okay, well, let's check it out. If x is equal to 4, then my series is going to be, and what will end up in the parentheses now? +1 to the n over 2n, which means pull the half out, and I'll be left with +1 to the n is just 1 over n. So that is, no longer has the property of being alternating. So what kind of series is that? Regular harmonic. And what do regular harmonics do? They diverge. So we do not include 4. So our final answer of the interval of convergence is 2 inclusive, but 4 not inclusive. You starting to get the hang of it a little bit? Okay. Okay, one more. All right, so same thing. For what values will this series finally converge? Apply our ratio test, check the endpoints. All right, so we'll do our ratio test. Parentheses, 10x to the n plus 1 over parentheses n plus 1 factorial multiplied by n factorial and 10x to the n. And let's take a look at what that simplifies to be. Okay, Jonathan, you want to try it?
10x times 1 over n plus 1.
Okay, good job. What will the result of that be? It's going to be 10x times 1 over infinity plus 1, which is 0. What does that mean?
The interval of convergence is all real numbers.
Correct. If the ratio turns out to be 0, it was a special case. If the ratio result is 0, then the interval of convergence is for all x values. So the interval of convergence contains all x that are members of the real, okay? So that's just another way to write all real numbers. Any x that's a member of the real number set. The little epsilon is like it belongs to or is a member of, or you could do negative infinity to positive infinity, or however you want to write all real numbers, okay? So the flip side of that is, what if the result of the ratio test would be infinity? It only converges at the center, wherever the center is, okay? That means the radius, okay, if the radius is infinity, then it only converges at the center.
Does it diverge everywhere else?
Mm-hmm. Yep. Okay, that concludes this module. I've got a couple things for the rest of our period today. I picked some multiple choice questions on AP Classroom because it's like you got to learn to pick the right one, because if you're off by even one, then you pick the wrong thing. Even you could have done a lot of work right. So it's like you cross your fingers almost for this to show up on the FRQ. Because on the FRQ, you can do all your work and get credit for all your work. If you happen to mess up one of your endpoints, you still get most of the points. But we're going to practice multiple choice. So we've got 40 minutes to do that. And then what I put at the end of these slides are just sort of putting everything all together. This is the book. When we purchase it, comes with like sample tests. I always write my own tests because I like them. I like to have control over what's on there. But I thought I'd give you a chance to look at what the book thought was. I didn't even get all of them. I did questions 1 and 2. I did questions 7, 8, and 9. And then I gave you the answers for you to check that. So let's start with the multiple choice on AP Classroom, and then finish coming back to this and finish these 5 sample questions, okay?